Alright, so let's talk about power functions. They come in the following format. They look like f of x is equal to k times x to the a, where k and a are rational numbers. So these are your power functions. So k and a actually have to be real numbers. They can't be variable. Well, 12, or I'm sorry, not 12, 5 of the 12 basic functions from chapter 1 are power functions. So can you think of 5, or let's just think of 1. 1 out of those 12 that can be written in this form. Something times x to the something. What's 1? X squared. So one of them would be y equals x squared. What's the second one? X cubed. So y equals x cubed. Think simpler. Very nice. That's not simple, but very nice, Mr. Buckman. Y equals 1 over x was your basic function, but can't that be written as x to the negative 1? There's nothing that says the exponents in a power function can't be negative. So there's 3 out of the 5. What's another one? Y equals, just y equals x. That's your linear one, right? And one last one. I thought this was the hardest one for you to come up with. This last one is the second to the hardest. Nope, that's that one. Y equals x to the 1/2 is which one? Which of the 12 basic functions is x to the 1/2? The square root of x, right? So any root, any nth root, is a power function. So if I asked you for the 8th root of x, that would be x to the 1/8. Any nth root, odd, even, it can be written as a power function. Okay? So k is your constant of variation. And you had constants of variation way back in Algebra 1-2 when you were doing direct variation and some of you inverse variation. I don't recall if you did it in 3-4, to be honest. So we might be reaching back 3 years, we have to remember that. A is your exponent. It's what we determine the power of the function for. Now, it is possible that your power function is a polynomial, by the way. So remember all of our translations. I mean, you could have a plus number out here that moves it up or down. That constant of variation, isn't it a vertical stretch or shrink? Right? And if it's negative, isn't it a reflection over the x-axis? So all of that still comes into play. But we could have something else added or subtracted here, just as a FYI. All right, so then we're going to determine example 1, whether the function is a power function, and if it is, state the power and the constant of variation. So A, 2x to the 4th, is that a power function? You read this form? I have something, remember that k and the a are actual numbers. They can't be variables. Well, there is a place where they might be a variable. We'll talk about that in a minute. So k, wouldn't that represent the 2? And then the a, wouldn't that be the 4? So isn't my base a variable? So that is a power function. It looks like a power. Kind of helps you think of it that way. So yes, what's the degree? Or I guess in this case our power. It's the exponent, right? 4. The power and the degree mean the same thing. So we looked at degrees of polynomial functions in the last section using that knowledge find the power. And then our constant of variation, CV, is what? What's the number in front of the variable? 2. The leading coefficient and the constant of variation are going to be the same thing. What about v? V equals 4/3 pi r cubed. I have a variable raised to an exponent. Is pi a variable? Or is it a number? It's an actual number, isn't it? So does this 4/3 pi really count as a number? So this actually is a power function. Nope. Oh. Very interesting point. Good point. Which pi is irrational. But your book is going to say that that's a constant variation. You're thinking. This is a thinking class. Now, yeah, good point. Doesn't quite match the definition there, does it? But I will guarantee your book is going to say 4/3 pi is your constant variation. But I got what you're saying. All right, so our power is what? 3. Our constant of variation is not just 4/3. It's the whole thing, 4/3 pi. Bless you. So I guess we should change that to a real number. Sure. Should be a real number. C. What do you think about C? If you say it is, I don't see the variable, which means I don't see the power. So what would it be? What is the degree of a constant or a constant value? No, not 1. Isn't the degree of a constant 0 because what's attached to it? X to the 0, right? So this is a power function. It's a constant power function. Its power is indeed 0. Its leading coefficient, or its constant variation, is what? It is 16. So that one you might want to highlight or star, because that's the one that you're probably going to miss. What about D? Yes or no? This right here is your example of an exponential function. There's the difference between a power function and an exponential function. So this one's no. They look very similar, but they're kind of reversed. In a power function, the base is the variable, the exponent is a constant number. Whereas in an exponential function, as this one is, the base is a restricted number, like in this case 5, whereas the exponent is the variable. So that one, not a power function. Then you're going to have to write power functions, and this is where I put some questions in your homework that might cause you to think a little bit. When you're writing a power function, so please write these with words. You're going to use phrases as varies directly, or directly proportional, varies indirectly, or inversely proportional. So you're going to be looking for those words to tell you that you have a power function. And those words separate the constant of variation from the power itself. And if you remember the definition of a power is really an exponent with, or a base with an exponent. The exponent is what we're calling the power of that function. So look at circumference of a circle. You should be familiar with that formula. C equals 2 pi r. The power is what? What's the power here? The variable is r, so its exponent is 1, right? If you see the variable but you don't see the exponent is understood to be 1. So that power is 1. What would be the constant of variation then? Yeah, this 2 pi, so include that pi, that whole 2 pi is your constant of variation. So we want to separate those two things with one of these phrases up there. So we're going to say 2 pi because it comes first. 2 pi. I like to use varies directly. Varies directly. As, and then you write the power itself, r. You're not going to write r to the first. So the power goes on one side, the constant variation. Area of a circle. What's the power? 2. Area of the power. What's the constant of variation? Just pi. So because they're being multiplied together again, I would be using the varies directly. Let's say directly proportional to. I like varies directly. So we've got pi varies directly as r squared. Now this is not written, the force of gravity one, this is not written in proper power function notation. So how would we write this so that there is no denominator? What? K multiplied by d squared? I can't just pull up the d squared without doing something else. If this moves up top, what happens to the... Nope.
That goes to
What happens to the exponent? It becomes negative, right? So doesn't this become k, d? I can't hear this well right there. You should sit here and try to listen to y'all out there. I have been complaining for 5 years. It just gets louder, and they keep telling me, it works perfectly fine. I said, no, it doesn't. And people walk in my room and go, wow, your air conditioning is really loud. You just go into your other rooms today and you just analyze. This is loud. When the air turns off, very silent. What? All right, so what's the power? -2 is the power. This is the weird one I was talking about. What's the constant of variation? It's whatever is not the power. So the power is the base and the exponents, if we consider the whole power together. So in this case, the k has to be the constant variation. Normally it's not a variable, but this is a formula. If we were using this force of gravity formula in a particular situation, that k is going to be a number associated with a particular situation where due to distance changes, that number k stays the same. Then if the situation changes, they'll change the k, but it'll stay the same for that particular situation. It'll keep changing the d. So my point is that sometimes the constant variation might actually end up being a variable if it's a formula. So how are we going to write this one using terminology here? K. These two right here varies indirectly and is inversely proportional, relates to your power being in the denominator. I like is inversely proportional. So K is inversely proportional to d squared. Now I'm not writing d to the -2. I'm writing d squared because the inversely proportional implies that it's in a denominator to that constant variation, yes. Yes. Both will give you the same thing. No. Don't do that. But a good thought. All right, so then we come to monomial functions. So some power functions are monomial functions, not all. So there are two forms that a monomial function can be in. f of x is equal to k. Remember, k was a constant of variation. Or f of x is k times x to the n. Well, is that any different than, let me see if I can fold this up here. Is this any different? Not cooperating. To this. These two. Are they any different? No, but note that this said are rational numbers, or we conclude it's really real numbers, right? Versus this says here that k is a constant, n is a positive integer. So, which of the following would not be considered a monomial function of these three up here? Would all of them be considered a monomial function? C is a constant monomial function, so yes. This is okay because we don't have a negative exponent, no negative exponent. What about your formulas here? These are all power functions. Which of these three formulas would not fall into this category? The force of gravity, because it has that negative exponent. So although this is a power function, it's not considered a monomial function. Because with a monomial, you cannot have a variable in the denominator. It's not a proper monomial. But yet it's a power function. All right? So determine whether the function is monomial. If it is, state the degree, the same degree instead of power, and the leading coefficient. So the same leading coefficient rather than constant variation. All one and the same. So, A. Yes or no? Yes. Yes, it is. It is a constant monomial function, is it not? What would the degree be? Very good. The degree is 0. What would be the leading coefficient? Remember, in front of this is x to the 0, right? Or behind that is x to the 0. So what's the leading coefficient? It is 23. Whatever the constant value is, that's your leading coefficient. What about B? Is B, does it fall into this category? First of all, is it a power function? Because all of these are power functions. Not all power functions are monomials, but all monomial functions are power functions. That's not even a power function because of the x and the exponent. So this is no. What about C? Yes. What is the degree? 6 is correct. And the leading coefficient? -4 is correct. So questions on that before we start to analyze graphs? Yes? Because the definition of a power function, not only a monomial, but a power function, is that the exponent must be a real number, the base must be the variable. So this one has it backwards. This is an exponential function. So you might want to write that here, that this is an exponential function. Which is not a power function. We'll use exponential functions for population growth and decaying later on. All right, so let's flip it. We only have 3 problems, and we're going to use all of this information, plus all the information that you learned in chapter 1, and we're going to apply it to each of these graphs. We're going to take some power functions, so we're going to start off with x cubed. You really don't need your calculator for this. You ought to be able to apply it without using your calculator. So if you don't know what values to put in there, just start plugging in values. Can I take 0 and cube it? What's 0 cubed? 0. What's 1 cubed? 1. What's 2 cubed? 8. So I'm going to go 2 off of my grid, and we'll stop there because I won't be able to fit any more on there. 3 cubed is 27, that certainly not going to fit. So then I'm going to draw my line through there. Can I cube negative numbers? Yep. So what's negative 1 cubed? Negative 1. What's negative 2 cubed? Negative 8. And again, I'm going to stop there. So this is the graph of y equals x cubed. We're going to answer a bunch of questions. What is the power of the function? 3. The constant they're referring to here is your k, your constant of variation. So all the way across here, just put in k. They're not asking what part of the graph is constant, they're asking for the constant of variation. So what is the constant of variation here? What's the number in front of the x? 1. So it's never the base of the power, it's the number that's in front of the base. So think of your domain. Remember with domain is x goes from left to right. So as I go from left, what is the leftmost x value? Negative infinity plus you to positive infinity. So the domain is unrestricted. And as you can see in the original function, there's no x in the denominator of a fraction. There's no x underneath a radical. The domain is unrestricted. So that makes sense. It would be negative infinity to positive infinity. Then for your range goes low to high. What is the bottommost y value? Negative infinity to positive infinity. So the range also is unrestricted. Just because the domain is unrestricted does not necessarily mean the range is, so you have to think about it. But there's no fraction here, so there's no horizontal asymptotes, no vertical asymptotes. So range is unrestricted. Increasing. Typically, we'll look at this origin here as the turning point. Increasing and decreasing always goes, the graph is going from left to right. Here's where you get some confusion. Because I'm going from left to right, I'm always thinking of the x value of the point at which the change from increasing to decreasing occurs. But I'm looking at the y value of the graph, whether it's going up or down, for increasing or decreasing. So we're going to focus on that turning point of 0, 0. So as I go from left to right, so negative infinity to the x value of 0. What's happening to the graph? Is the graph going from low to high or from high to low? Low to high. So is that increasing or decreasing? Increasing. So that part's increasing, negative infinity to 0 on the x-axis. Then from 0 to positive infinity on the x-axis, what's the y doing? It's going from low to high. So isn't that increasing again? So isn't the entire graph increasing? So from negative infinity to positive infinity is where the increasing is occurring. We don't need to put 0 in there, because there's no interruption of the increasing of the graph. It goes from increasing, does a little loop-de-loop, to increasing again. Now it's possible on some of these cubic functions that you can have a real S-curve to it with a relative max and min. Then you'd have to find the relative max and min, and the x value of the relative max and min will tell you what increasing and decreasing starts and stops. So you might run into that. So remember our translations, if we have a coefficient in front of this, or if there's a plus or a minus here, that can affect the curve of that S. And you could have a cubic that has increasing and decreasing associated with it. This particular one doesn't. So we'll put none. Odd or even. There's 2 ways you can figure it out. Take your original function, and I'm going to go down below here, and I'm going to take f of negative x, so I'm going to plug in a negative x into the function, and instead of x cubed, I'm replacing x with a negative x. What's negative x cubed? Negative x cubed. So I get a negative x cubed, I started with a positive x cubed. Didn't all signs change? There's only one term. Didn't all signs change? If all signs change, what is it? It is odd. If no signs change, it's even. If you can't make a sign change one way or another, which we'll see here in a minute how that occurs, then it'd be neither. Then look at the symmetry of the graph. Isn't the graph in diagonal quadrants to itself? That's a hint that it would or could be symmetrical to the origin. So if I were to reflect this over the y-axis here, wouldn't it go this direction? I this. And then if I were to reflect this over the x-axis, wouldn't it reflect onto this here? So that double reflection means that it is symmetrical to the origin. So one of those two methods both tell you that it's odd. So it is an odd function. Is it bounded? Usually we look for some maximums or mins, but it's an overall max or min. You can have a relative max or min and it's not bounded. Is there a definite bottom to this graph? No. Is there a definite top to this graph? No. So is it bounded? No. So this is unbounded. So you want to put none or unbounded. Extrema, that would be relative max or mins, or overall max or mins. Was there any of that here? No. So none. You'll want to leave it blank. Asymptotes, that could be vertical or horizontal. There are no fractions in this. No variables in the denominator. That creates vertical asymptotes. There's no numerator and denominator to compare degrees with, so there's no horizontal asymptote. So there is none. Then you have got to get used to how the end behavior is written. You have to look at the right-hand behavior and the left-hand behavior. So the right-hand behavior would be as we approach positive infinity, that's right-hand, it's going to the right on the x-axis. So it looks like this. The limit as x approaches positive infinity of the function is x cubed equals. So as x approaches positive infinity, what's happening to the y? Because the equals is always your y. What's it approaching? Going up infinitely, right? So what's y approaching? Positive infinity. So this is your right-hand behavior. As x approaches positive infinity, y is approaching positive infinity. It's going up. Look at your left-hand behavior, meaning we're going to the left. We're going towards negative infinity. So the limit as x approaches negative infinity of the function, which is x cubed, equals. So as I go to the left, here's negative infinity over here, what is happening to the y value graph? As I go left towards negative infinity on the x-axis, what's happening to the y value? It's going down, which is negative infinity. So it is approaching negative infinity. This is your left-hand behavior. The right-hand behavior does not agree with the left-hand behavior. That will become important later on. But you're getting introduced to it now. Questions on that? All right, so let's look at another one. Let's look at square root of x. How else can that be written? X to the 1/2. So let's go ahead and plot some ordered pairs. Can I plot negative values? Can I take the square root of negative values? No. Can I take the square root of 0? Some of you don't realize that. Yes, I can. What is the square root of 0? 0. What is the square root of 1? 1. 1 is a perfect square. Some of you don't realize that either. What is the next perfect square? No, that's where negative 1 can't make square root. 4. So the next perfect square is 4. What's the square root of 4? 2. So there we go. So then this is y equals x to the positive 1/2. And I write it that way on purpose so that we can now see what is the power. 1/2. What's the constant of variation? The number in front of the variable is 1. What's the domain? What's my leftmost x value? 0. And it's a bracket because we are including 0. You can take the square root of 0. And it goes to what's the rightmost x? Positive infinity. What's your range? What is your lowest y value going from low to high that you can do? 0. A y value of 0 at that order pair 0, 0. So your y value is 0 and it is included because it's a point on the graph and it goes to what highest y value? Positive infinity. So it appears that the domain and range are identical. Increasing. From left to right is the graph increasing. Where is the first start of the increasing? Right there, the x value is 0 because we're going from left to right. That's the x value on the axis. So we have increasing at 0 and including 0. And it continues to increase through what number? Positive infinity. It never stops increasing, right? Does the graph decrease? No. Remember, this graph is going from low to high always. So there is none for decreasing. Is the graph even or odd? Well, let's look at the symmetry. Is it symmetric to anything? Is it symmetric to the y-axis? That would make it even. There's nothing over here, so the answer has to be no. Is it symmetric to the origin? Is there anything over here? Is it being diagonal quadrants? No. It cannot be symmetric to the origin. So if it's not symmetric to those two, what is it? It is neither. And think about it this way. Can I replace x with a negative x? Can I take the square root of a negative x? No. I can't even perform it, so therefore it's neither. Is it bounded? Does it have a definite bottom of the graph? Yes, where at? Right here at 0, 0. So it is below, at the bottom, isn't it? Do I have a definite top? No, because it keeps getting higher and higher and higher. So this is bounded below. Is there any extrema? We wouldn't normally call this a minimum, but it definitely has a minimum value, doesn't it? Because of that boundedness, isn't this the limited or the minimum value right here at that point? That point right there is actually your extrema. And so watch how we write it, because your book or your homework is going to ask this question in a very interesting way. I always write my extrema. The extrema is it a max or min? It is a minimum because it's at the bottom. A minimum of, what's the y value of the minimum? 0 at x equals 0. So it's a minimum of 0 at x equals 0. If you always write your answer to maximums and minimums that way, you will never go wrong in your answer. Don't write it as an order pair. Asymptotes. Is there a fraction in this problem at all? There's no asymptotes now. None. End behavior. How many ends to this graph are there? This is not really an end, this is a start. So the end is to the right. So there's only right-hand behavior on this. And as we go to the right, we approach what number? Hit positive infinity. So it's written this way. The limit, as x approaches positive infinity, that implies I'm looking for the right-hand behavior because I'm going to the right, of the function, which is the square root of x, equals. So as I go to the right, what's happening to y? It's approaching positive infinity because it's going up. So this only has right-hand behavior. There is no left-hand behavior. Last one. Cube root of x. Interesting one to graph. You haven't graphed this one before, but you can graph it. So let's think about this. Can I take the cube root of 0? Yeah, so what's the cube root of 0? 0. 0 is its own cube and its own cube root. Same thing with 1. What's the cube root of 1? 1. What's the next perfect cube? 0 cubed is 0. 1 cubed is 1. What's 2 cubed? 8. So I want to put 8 underneath that cube root. So my x value is 8. So I'm going to go slightly off here. What's the cube root of 8? 2. That's as far as I can go on this graph. So it's almost like the cube root graph, but isn't it turned on its side? And kind of flipped a little bit. It's turned this way and flipped this way, reflected. Can I put negative values underneath the cube root? Can I take the cube root of -1? What number times itself 3 times gives you -1? -1 times -1 is positive 1 times -1 is -1. You can take the odd root of a negative number. Odd roots are unrestricted in your domain. It's the even roots that are restricted. I cannot take an even root of a negative number, but I can always take the odd root of a negative number. So I can take the cube root of -1, which is -1. So what's your next perfect negative cube? -8. So if I go to the left, -8. What's the cube root of -8? -2. So then the graph gets drawn that direction. So this is y equals x to the, and I'm going to write it to the 1/3 in power function notation. So what's my power? Everybody says 1/3. What's your constant of variation? 1. Now they're going to put something in front of that on your homework, just to let you know. What's my domain? What's my leftmost x value? Negative infinity to my rightmost, positive infinity. So note that I talk to myself a lot. Yes, I'm certified with nuts. So this is how you should be talking to yourself when you're doing your math. You'd ask yourself these questions. I say it over and over again for a reason, because we're still getting domain and range wrong. And I continue to do it the same way. What's your leftmost x value? What's your domain? What's your rightmost? What about range? What's your lowest range value? It's going to be negative infinity to positive infinity. If I sat next to each one of you and did that with you individually, you'd get them right most of the time. So you got to learn to talk yourself through it. All right, increasing. As I go from left to right, what did my turning point be? 0, 0. So as I go from negative infinity to the x value of 0, is the graph going from low to high or high to low? Low to high. So is that increasing or decreasing? Increasing. So then from 0 to positive infinity on the x-axis, is the graph going from low to high or high to low? Is that increasing again? This is the whole graph increasing, just like the x-cubed graph. So we're increasing from negative infinity to positive infinity. Are we decreasing? Nope. So there's none on this one also. What about odd or even? If I were to take, so we're going to do it all the way down here, f of negative x, and put that into the cube root function, and I try to take the cube root of negative x. Well, let's assume x is a perfect cube. What would my answer come out to be if this value under here is negative? When I get a negative whatever out of there, obviously x is not a perfect cube right there, but I would put a perfect cube underneath there. And I would get a negative value. Doesn't that change the sign here? From a positive to a negative whatever it happens to be. I mean, I guess technically you can look at it as negative cube root of x, because whatever x is, we would actually take the cube root out, but it's going to be a negative answer. It changed the sign. What kind of function is that, even or odd, when signs change? Odd. Look at the symmetry. Is it symmetrical to the origin? If I were to reflect this over the y-axis, it would look like a bird in flight right here, and then this gets reflected over the x-axis, it will become this part here. It is symmetric to the origin, so it matches the symmetry test and the algebraic test here. So it is odd. Is there a bottom to the graph? A top? Nope. Is it bounded? No. So it is unbounded. Is there any extrema? No. It is possible with this cube root, if there's a vertical stretch or shrink, that you could end up with a nice little S-curve in there where you could have some relative max or min, so do watch that. So there is none on this one, though. Asymptote. So are there any fractions to this problem? There's not going to be an asymptote, so none. End behavior. Are there two ends to this graph? Yes. So there's two end behaviors, one for the right and one for the left. So as x approaches positive infinity, so as we go to the right, what is the y value doing? Approaching what? It's increasing, so it's approaching, and this is a cube root function. It's approaching positive infinity. This is your right-hand behavior because we are approaching positive infinity. Then, if we go to the left, which would be your left-hand behavior of the graph, we are approaching negative infinity on the x side. So as x approaches negative infinity of this function, what is happening to the graph as I approach negative infinity? Is the y value doing what? It's going down, it's approaching negative infinity. So again, your left-hand behavior and your right-hand behavior do not agree. Question. Up here, or down here? You want that up? Huh? I know, sorry. I'm tall. I'm his way, or sometimes his way, or your way. I can't make myself shorter. Then I'd be like this. Trying to do no toilet here. Oh, you mean when you're writing this, do you have to put, could you put extra one there? Yes, you could. Yeah. Get used to the notation because you need to be able to read it and understand what they're asking. If they ask for a limit as x approaches infinity or negative infinity, they're asking you for your right hand or left hand behavior. So I keep throwing it at you in the hopes that you're going to start to recognize that. Are there any other overall questions? Yes. The extrema would occur if I had a definite lip, like a mountain or valley in here. So let's take this and let's change it, give it some sort of stretch to it. So, I don't know, let's make it really big, like, let's try 5. Parentheses, I'm doing a cube root. Where's math? Math. Cube root of x. Let's see what that does to our graph. I still didn't get it on there. But you're going to come up with some in your homework. I'd have to mess with it for a while. But where this ends up being, and it's really more likely you'll see it on this one. So we could maybe change it to the cubic one. So 5x cubed. Let's see what that one does to it. Nope, still didn't do it. We'll have to add some. Let me add this to it. How about minus 2x plus 3? Now that's no longer a monomial function, but it is a power function still. But do you see where the max and min now occurred because I added in the x term? So it could happen. They're giving you all monomials in your homework tonight. So we'll explore that as we go further along. But for right now, your extrema, they could do the x squared function on you. That's where you're going to have a minimum or maximum, right? So out of these 5, this is the one you're most likely to see the max or min on, or the square root function for right now. Any other questions?